So this is our third lecture on psychrometrics. It's in the chapter on ideal gas mixtures, where we had general mixtures of ideal gases. We were able to solve problems for open and closed systems. Well, guess what? We've covered the temperatures, the humidities, and now we're ready to solve some problems where we have moist air as our ideal gas mixture for both the closed and open system. So here's the problem. So moist air at 40 degrees C, 100 kilopascals, 75% relative humidity is contained in a 2.5 cubic meter rigid closed tank. The tank contents are cooled. So determine the heat transfer in kilojoules, so Q and the cooling process in kilojoules, if the final temperature is 35. So you cool from 40 to 35. How do you solve that problem? First thing, first law. First law for the system. So you have a rigid tank. The system is the contents of the tank, which is the moist air inside the tank. So the first law would say the final internal energy of the system minus the initial internal energy, neglecting changes in kinetic potential energy, is equal to the heat transferred into the system during the process. But what is the direction of the heat transfer? Q1 to 2. Can I modify that and say I want to talk about a positive heat transfer out of the system? Can I put a negative sign right there? Say it's out of the system. Sure. Now I'm talking about a positive answer, and I know the direction. It's like drawing a free body diagram and putting the direction of the force that assumed the direction of the force. All right. And then what was our traditional direction for the work? Out of the system. That's why there's a negative sign on it. And is there any work for this system, or is the work equal to 0? And why? Because it's a rigid tank. There's no boundary work. There's no paddle wheel or electric power or anything. So the Q1 to 2 is U1 minus U2, which would be if I have either the mass of the dry air times U1 minus U2 of the dry air plus the mass of the vapor, U1 minus U2 of the vapor. You say to yourself, well, some of that vapor could condense, and then I would have to modify it. It would be in liquid form. I don't know if it all stays in the vapor form. What of the three temperatures can I compute to see if it will condense or not, and compare it against this 35 degrees C? You calculate the temperature dew point, and it's around 34.5 or something. Let me look at my notes. 0.5 degrees C. So do you expect anything to condense? No, the temperature's above. So this is a good form to write where it's all remains vapor. Part B, guess what we're going to do? We're going to cool it below the dew point. But let's do part A first. So how do I calculate the mass of the dry air in a container that is this size? That's the volume in the container. And it has 75% relative humidity, 100 kilopascal, and 40 degrees C. How do I determine that mass of the dry air? Use the ideal gas law. And so we'll write it like this. We'll say, okay, let's do this. The mass of the dry air, is that equal to the partial pressure of the dry air in the mixture, initially at state 1, times the total volume of the container, times the molar mass of the dry air, divided by R bar T. Hey, I'm getting pretty good at this ideal gas equation, aren't you? Yeah. And so you say, okay, how do I get the molar mass of dry air is easy. R constant, that's easy. This temperature is 40 plus 273. The volume is known. How do I get the partial pressure of the dry air? If the total pressure is the partial pressure of the dry air plus the vapor pressure, what's the vapor pressure? Relative humidity of 75% times Psat at the temperature of 40 degrees C. True? Yeah. So bing, bing, bing. Yes, sir.
Do you also use the volume from the dry air, or do you use total volume?
This is, okay, that's a good question. This is a total vol. All questions are good, sorry. All questions are good. But it's the total volume, because it's the partial pressure concept. You go back to Dalton's model, it was as if it's all at the same temperature and volume of the mixture. You're right. No, don't mix and say, well, I have a partial pressure, maybe I need a partial volume. No, no, no. Either go with Dalton's or Amagat's. And typically we like partial pressures. Got it. All right. So this mass we calculate. How about the mass of the vapor? How do you get the mass of the vapor? Ideal gas equation, just like you did the mass of the dry air. Are you serious, Professor? So the mass of the vapor is the partial pressure that the vapor exerts, the total volume, the molar mass of the vapor, R bar T. And this V is the same as this V. This T is the same as this T. This R bar, well, of course the R bars are the same. And is this PV that? Yeah, sure. So there we go. We have the masses. Now, where do we get the internal energy U of the dry air? Both at this U1 is the dry air internal energy at a temperature of 40 degrees C. And this one is internal energy of dry air at 35 degrees C. Where do I get those? Air table. And so if I look it up, then we get that this one is (223.52 kilojoules per kilogram, as well as 219.93 kilojoules per kilogram. I know it's in Kelvin. You have to do a little interpolation. There you go. What about the vapor? How do I get U1 of the vapor? Well, how do I get that? Use of G at that temperature of 40 degrees C. And how about U2? Use of G at the temperature 35 degrees C. And what table do they come out of? A2. Yeah, our steam table. Right. Yes, sir.
What's the difference between A2 and A23 where it has that one big one?
You can use either table A23 and it'll give very good answers, or table A2. Either one will work. I encourage you to do it both ways. Table A23 is on a kilomole basis. So I'd have to get the number of moles. Well, how many number of moles of vapor are there? Well, it's the mass of the vapor divided by the molar mass, 18.02. Yeah, and there you go. Yeah, but now don't do this. Don't use, for the same problem, some data out of table A22. Let's say I want to get U2 out of U2 bar out of table A22. And I'll get U1 out of table A2. Why will that not work? Different starting point, different reference state. That's exactly it. In the steam table, it was something like the saturated liquid's internal energy at the triple point is arbitrarily set to 0 as for energy measurements. I think that's right. Somebody want to check me? Maybe I should check it myself. Here, I'll check myself real fast. I don't want to say something wrong. So we'll just take a look real fast. Yes, the saturated liquid's internal energy is set to 0 for steam. All right, so that's the starting measuring point for energy in table A22 or A2. What about A22? It's like extrapolated down to 0 Kelvin. Okay? They stop at just temperature of 200 Kelvin. That's pretty cold. And yet it still has a significant H and a significant, this is for vapor. Oh, no, it is actually. They show it. They show 0 Kelvin has 0 H bar and 0 U bar. When you run the numbers, what we find is that it's equal to, the first is 9.44 kilojoules of energy. The second term, 0.64 kilojoules of energy. So when they combine them, we find that the Q is equal to 10.08 kilojoules, 10.1 kilojoules. And you can go back and say that it was 94% associated with the cooling of the dry air, and the other percentage of 6.4% of cooling, 93.6 if you want more exact, 93.6% cooling the dry air, and 6.4% of the heat transfer is associated with cooling of the water vapor. Ready to move to part B? So, what happens if you cool it to a temperature that is T2 is less than the original dew point temperature? What's going to happen to some of that vapor? Going to condense. So let's go ahead and we'll do the first law analysis. The Q, 1 to 2, will be the mass of the dry air times U1 minus U2. That hasn't really changed. The only thing that really changes is the final temperature is now 30 degrees C, not the 35 degrees C. So that's changed. Then you're going to have the mass of the vapor that stays vapor. So I'm saying the mass that is vapor at the end of the process, at state 2. We're going to have to work to get that. And that is going to be U1 minus U2, all vapor. And then we're going to have the mass that's in the liquid state at the end of the cooling process, because that started at U1 and it ends at a much different U2 for what eventually is liquid. Okay, so what starts in the liquid, whatever ends in the liquid, but what it starts with, this is the same, because everything's vapor. Some of it stays vapor, but some of it ends liquid. Okay, and so this U1 and U1 here is U sub G at the temperature of 40 degrees C. This is U sub G at the temperature of 40 degrees C. But what is U sub 2? That's U sub G at 30 degrees C. And what about this U2 for the liquid? U sub F at 30 degrees C. True? Okay, so the mass of the dry air didn't change. And what we have to do is we have to calculate this mass here. Well, how are we going to calculate the mass that's in the vapor state at the end of the cooling process? It's saturated air at that lower temperature. So you're going to say, I'm going to use the ideal gas equation, PV, total volume, molar mass of V over R bar T, and PV is equal to P sat at the 30 degrees C, because it's saturated air. That's what everybody follow that? All right. How do I get now, though, the mass that's the vapor? How do I get, the mass that's liquid at the end of the cooling process? Conservation of mass. You already calculated from part A what started in the vapor state, and you subtract out what ends in the vapor state. The difference is what is the liquid. So maybe I should do that. MV1 minus MV2, and there you go. What we find is that not a whole lot of the vapor condenses. We find that by mass, the mass fraction, 79% stays in the vapor. But by mass, 21% goes to liquid, condenses. So about a fifth of the water vapor condenses in this problem. Yes?
That MV1 minus MV2, MV1 refers to the mass of vapor from part A?
Yep. That's exactly it. The same mass that we started with at part A. Like this mass of the dry air is the same from part A as well. So when we put in our numbers, you find that there's a 18.87 kilojoules plus 1.02 kilojoules plus 45.93, all that kilojoules, to give a total cooling required of 65.82 kilojoules. So compare before. You went from 40 to 35, 40 to 35. That required 10 kilojoules of cooling. You went only 5 more degrees, 35 down to 30. It's not an additional 10 kilojoules making it 20 total. No, it's 55 kilojoules more, making the total of 65.8 kilojoules. Why so much more? Takes a lot of energy to condense water vapor. It's just, there's a high enthalpy of vaporization or heat of vaporization. I know we're seeing it for a closed system. It's a U, internal energy. So this turns out to be about 69.8% of the total, only about 1.6% of the total Q, and 28.7%. Good? Good to go? Let's press forward. Now we need to do an open system analysis. Well, open system, there'll be some sort of control volume. The simplest is just a M dot with the system 1 coming in and a 2 going out. So single inlet, single outlet. The other one we want to consider is where you have inlet 1, state 1 coming in, inlet state 2 coming in, and 3 going out. And you know what? I'm going to leave it to where you do the next one. So this is mixing and the other would be splitting, but splitting's real easy. So let's just do the mixing. What we're going to do is an air balance for both of these. So if I do a control volume and I say, is there conservation of dry air in the system? Yes or no? Yeah. And so what would the dry air balance look like? You'd say the mass flow rate of dry air coming in at state 1 is equal to the mass flow rate of dry air going out of state 2. When you have a single inlet, single outlet, you can just dispense with it, just call it the mass flow rate of the dry air. It's the same through the system. How about if I have this mixing? This is mixing. Well, then you have the mass flow rate of dry air at 1 plus the mass flow rate of the dry air at 2 equal to the mass flow rate of the dry air at 3. All right. That's pretty straightforward. What about the water balance? Well, I'm going to have the mass flow rate of water coming in at 1 plus any M dot inlet. It's anything added into it. Maybe I bring in some water like this and I spray it in. True? Okay, that's equal to the mass flow rate of the water vapor going out plus any that I may collect and come out in the liquid form. So typically M dot, this is the mass flow rate of water coming in, and then we have the mass flow rate of water exiting or out. Okay? Plus M dot water out. Both of these are water. It's a water subscript. I got a lot of subscripts, right? But you can see it. So what do we have? If you have this as positive, that's called humidification. Okay? Typically you don't have both humidification and dehumidification occurring at the same time. Either you're going to spray some liquid water or some steam into the system, that's called humidification. Or you put a cooling coil, a cold surface in there, cold evaporator coil, and then you need to have a little catch tray on the bottom to catch the liquid that's going to go out. Well, what is that doing? That's called dehumidification. There you go, dehumidification. So you can write this general equation. Both of those terms aren't going to be non-zero at the same time. But some problems you'll have dehumidification, some problems humidification. Well, what is a good way of writing this M dot water in? Well, it would be the humidity ratio in times the mass flow rate of dry air in. Isn't that give me the right vapor flow rate coming in? Sure. And then which one do you want to do? Should we run one, like an example, humidification or dehumidification? Which one do you want to try and do as an example? Both? Well, then I got to write twice. Okay, so HUMID, humidification, and dehumidification. So for humidification, then we have the mass flow rate. I'm going to say of water in equal to humidity ratio out times the mass flow rate of dry air out. Are these two mass flow rates of dry air the same? So we get rid of the subscript 1, 2. And then we see, oh, there's a relationship. The mass flow rate of the water coming in is equal to the higher humidity ratio minus the lower inlet humidity ratio times the mass flow rate of dry air. And then you do it also for dehumidification. You say the m dot of the water going out will be, I come in with a high humidification, go out with a low absolute humidity or humidity, oh man, I'm skipping here. Humidity ratio, omega, times the m dot dry air. So either way. Very similar equations. All right, what about mixing? Well, you're going to have mixing plus dehumidification. But let's say I don't have any dehumidification or humidification. All I have is omega 1 m dot dA1 plus omega 2 m dot dA2 equal to omega 3 m dot dA3. Typically you mix and then you move to another and then you dehumidify, or you move to another and you heat or cool and humidify. All right. What about an energy balance? Didn't leave a lot of room for it, but the energy balance would be, let's do this. I have either some heat transfer in or out of the system. Let's do this. Let's call it positive Q dot into the system. So Q dot into the system equal to the mass flow rate of the dry air times the H exit minus H inlet of the dry air. And then you're going to have the water, which gets a little complicated. I can't write it for both dehumidification, humidification. I just need to pick one. But let's write it for what? Dehumidify? All right, well, it's just like what we wrote before. You have the mass flow rate of the dry air times the humidity ratio going out at 2 times the enthalpy exit minus enthalpy inlet of the vapor. This is water vapor. Plus, and then we're going to have the mass flow rate of the dry air times omega 1 minus omega 2. What does that give me? That gives me how much is dehumidify, how much is the liquid flow rate. Isn't that the liquid flow rate? Times the inlet enthalpy, or no, exit enthalpy, H, maybe I should call it 3, H of the liquid going out. If you're dehumidifying, it's going to come out liquid, minus H of the vapor coming in at 1. Well, a very similar energy balance over here for the mixing. Okay? Let's solve a problem. Air at 12 degrees C, volumetric flow rates given, relative humidity is given. It's being heated and humidified. And it exits at, can you see that it exits at a higher temperature? And it exits even at a higher relative humidity, but if you're humidifying, it's the humidity ratio that really goes up. All right. Liquid water at 25 C is supplied to the humidifier. The pressure is 101.3 kilopascal throughout. What is, for part A, the mass flow rate of the dry air entering the coil? How are we going to get the mass flow rate of the dry air?
Relative humidity.
We do it so many times, right? The mass flow rate of the dry air would be the volumetric flow rate of the total moist air times some density or divide by the specific volume of the dry air. You use the ideal gas equation. The density of the dry air is equal to partial pressure of the dry air, the molar mass of the dry air divided by R bar T of the mixture. I know that this is ideal gas equation. You just need to be good at it, right? But how many years have you been old friends with the ideal gas equation? Long time. Long time. All right. So that gives us the mass flow rate, about 37 kilograms per minute. That's the mass flow rate of the dry air. Is that the mass flow rate of the moist air? No, only the dry air. Okay. What is the flow rate of liquid water supplied to the humidifier? How do I find that supply of liquid water to the humidifier? If you do a water balance, the water balance, basically the m dot liquid coming in is equal to the mass flow rate of the dry air times the difference in omegas, humidity ratios. It's going to go out higher than it came in, lower. So maybe I should have made a little sketch, put it like this. Comes in at state 1, goes out at state 2. And maybe you bring in some liquid water and spray it in. And then maybe you bring in a hot coil and there's heat added into it. It's heated and humidified. All right. So how do I get the omega 1 humidity ratio inlet? Yeah, we've done that a number of times, haven't we? So 0.622 PV over P minus PV. What is PV1? This is 1 equal to phi times P sat at T1. Phi1 times P sat T1. And the same type of equations to get omega 2 using PV2. So it's like done, done, done. And that's how you calculate 0.345 kilograms per minute. Now, every now and then I encourage students, it's hard to do, I appreciate this, to say, is this number, roughly in the right ballpark, or how much is this? So if you have a water bottle, a 1 liter water bottle, it's about a third of the water bottle per minute. It's not a lot of water, but that's what this problem shows. Okay. What is the rate of heat transfer to the moist air? So now we got the moisture. What is the Q going in? Maybe I draw it like this. Q dot going in. Well, you do an energy balance. Q dot going in. You can break it into 3 components. One is the mass flow rate of the dry air, and it goes out with a higher enthalpy than it came in because it's hotter, isn't it? What else? We have the mass flow rate of the dry air times omega 1. What's that coming in? What's that, the mass flow rate of the vapor coming in the inlet stream? And that's going to be heated, so that's going to be H2 minus H1 of the vapor. And then you have the mass flow rate of the liquid, but that's coming in. It goes out H2 the same. It goes out in the vapor state, but how does it come in? H1 in the liquid state, doesn't it? So those are the 3 contributions to the energy balance. Okay, so how do I get the enthalpy of the dry air at the exit temperature? This is enthalpy dry air at, what temperature is it going out at? 32 degrees C. This is the enthalpy of the dry air at 12 degrees C. How do I get those two? Air tables. Professor, could I use C sub P delta T, make life a little easier? Sure. That'll be very accurate as well. Encourage you to do it both ways in homework so you're very familiar. How about this enthalpy in at state 1? Isn't that Hg at 12 degrees C? And is this Hg at 32 degrees C? Yeah. And is this H2 of the vapor equal to that H2 of the vapor? Are they the same? They both go out at 32 degrees C, and they're both vapor. And this one's a little tricky. That's going to be HF at the supply temperature of the liquid water, 25 degrees C. All right, so when we run this problem, we find that, yeah, you use a little more energy. What we find is that, let me just uncover it. What you find is that there's 26.5 kilowatts total. This is 26.5 kilowatts, of which about half of it's to heat the dry air. And a negligible amount is 0.2%, is pretty negligible, to heat the vapor that initially came in the air, in the inlet stream. And a whopping, surprising 53% of that heat, off that heating coil, to get that liquid that was sprayed in up into the vapor form. Takes a lot of energy to vaporize. True? Comments on that? I'm going to go ahead and stop. Thank you for your attention.